I first present you the YouTube transmission, I mean. Quando você começar, você me avisa, tá? Okay. Hi, everybody. Thank you to come here at YouTube platform to see the presentation by Malin and Svensson Lundmark from Lund University. And on behalf of the ISPRA Speech Prosody special interest group, I welcome Malin here to talk about segmental articulations and prosody. Malin got his PhD in 2020 from Lund University, and now he is a visiting scholar, researched at Queen Margaret University in Scotland. And thank you so much to be here with us, Malin, and the floor is with you.
Thank you so much. So I'm very excited to give a talk at this Prosody Lecture series. So my name is Malin. I was academically raised in a prosody environment at Lund University, working on Swedish word accents. But I've shifted more towards articulation, and now I'm very eager to use movement dynamics to examine prominence and break patterns in speech. So this talk is about segmental articulations, and this is about how the articulators are joining forces in creating the acoustic segments. So when we work on speech prosody, I think it's very good or extremely important to understand the relationship between the articulator and the segment. So I will start with diving into movement dynamics. So basically, we're back at school in physics class. An object's position moves as a function of time. If the object is attached to a string and the string is stretched, the object begins to move. You add energy and the string itself adds energy. And if no new energy is added, the object will slow down and eventually return to its original position. So the object has its fastest moment as it passes the starting point, and then it decelerates just before it changes direction. After it has changed direction, it gains speed again, accelerates before it again reaches peak velocity. So you can divide the movement really into fast and slow intervals. The fast intervals is when you have peak velocity, and the slow intervals or steady states, that's when the object changes direction, and that's when it decelerates and then accelerates. We can compare this movement to an articulator. Perhaps the articulator does not have a string attached to it, but its movements follow this as well. Here we have movement patterns of lips. This is a lip aperture where we measure the distance between two EMMA sensors on the lips. And EMMA, it's short for electromagnetic articulography, which is a method to get position and time data of the articulators. Both the ones we can see, such as the lips, together with the ones we can't see inside the oral cavity. So we have the distance between these two sensors, meaning the lips are either open during the vowel or they are closed during the constriction. And here it is a bilabal segment, M. So the fast intervals are divided by these steady states. It's the same pattern as for the object attached to a string. There are some points of deceleration and acceleration. These divides the fast from the slow intervals, and these are really acceleration peaks. So I want to say also, please note that throughout the presentation, I sometimes referred to both the deceleration and acceleration peaks as acceleration peaks. And I also use the word posture and steady states interchangeably. So, but now let's look at what these deceleration and acceleration peaks really are. They are deceleration peaks and acceleration peaks are moments in time when we find a lot of articulatory changes. Not only is speed changing the most, also direction of an object, and there are also jerky movements. So here on the bottom row is the EMMA signal of a sensor attached to the tongue tip. as it moves over time in vertical dimension, so up and down. And this signal is from one speaker saying the word malar in Swedish. And now I thought that everybody might want to try to speak Swedish and produce this word. You can repeat after me. Malar, malar. So you may find that your tongue tip moves up, stays a while before it goes down again. So this is the position signal we see at the bottom of the figure. When it's moving up and down, the tongue tip moves very fast. That's where we find velocity peaks on the second row from the bottom in the figure. And just before the tongue tip gets into position, it slows down really fast. That's a deceleration peak in the acceleration signal. And when the tongue tip leaves the position, it changes direction and speeds up very fast. That's an acceleration peak. So the deceleration peak and the acceleration peak are on either side of this tongue tip posture. And you may notice the peaks on the jerk signal too. That's the top row in the figure. Mathematically, the third derivative to position. So at the time of the deceleration and the acceleration peak, we also see jerky movements at the start of the tongue tip posture and at the end of the tongue tip posture. There's a lot of changes at these points in time. There's an image of roller coaster here. So roller coaster rides are designed to stimulate the human sensory system. Jerk and acceleration play a massive part to the experience of the roller coaster ride. So I hope to show you today that these moments in time, the acceleration and deceleration peaks, play a significant role also in speech production, which has an apparent link to acoustics and perception. So now let's get into segmental articulations. So let's just state the obvious. What are segments? Here to the right, you see the Swedish word namnen, which means the names. It has a cluster in the middle. So this has been manually segmented. We see the formants and also F0 in the figure. There are, of course, different strategies to segmentation, but we all do it because segments are important. But the segments in themselves can be viewed as dead intervals, meaning the segments are steady states shaped by the articulator, which really provides the listener with no new information. So in the word to the right, the tongue tip shapes a steady state 3 times in initial, medial, and final position of the word. So dead or not dead, as we already know, there is a lot of movements just before and after each of these steady states. And that is what is referred to as the transition between the segments. These transitions provide the listener with information about the coordinated articulatory movements. And it has been shown that listeners use this information, for example, in vowel identification tasks, as in the silence center paradigm, where you mask the vowels and the listener make use of the transition into the vowel. So in other words, segment transitions play a big part in understanding speech. Segment transitions are rapid articulatory movements. These rapid movements cause acoustic changes, which we then mark as segment boundaries. This relationship is already well known, but the nature of the rapid movements has gone quite unnoticed in phonetic science. Here's a figure again on some EMMA data. So this is a calculation again over the distance between the 2 lips. This time you have the position signal in the middle instead of in the bottom of the figure. And the lip aperture signals show that the lips are closing, shaping a steady state, a posture of the lips. And before and after the steady state, there are fast movements. That's peak velocities, 2 peak velocity on the velocity signal in the bottom of the figure. And between a velocity peak and the steady state, the lips are either slowing down rapidly, that's a deceleration peak, or they are gaining speed rapidly, that's an acceleration peak. So how about we add these rapid movements and form an hypothesis to be tested, which is that there is a one-to-one relationship between articulation, basically acceleration peaks of a crucial articulator, and acoustics, segment boundaries. So I highlighted the word crucial here because articulators shape postures all the time during speech. And this hypothesis would only apply to crucial articulators. So what is a crucial articulator? Well, it refers to that articulator that articulates the onset and the coda of the syllable. So for example, for N, a crucial articulator is the tongue tip. For P, it's the lower lip. And for K, it would be tongue dorsum. And this stems from the CD model, the crucial articulator. So for example, in this figure, we see a Swedish word, manna, segmented at the bottom of the figure. And we have position and acceleration signal of two articulators, lips, or actually lip aperture, and at the top and tongue tip below. So for the first segment, which is bilabial, the lips are closing, creating a posture. They are the crucial articulator for M. In the acceleration signal, we see a deceleration peak at the start of the posture because the lips are rapidly slowing down. And at the other edge of the posture, we find an acceleration peak, meaning the lips are rapidly gaining speed. On the tongue tip word initially, we see neither a posture or acceleration peaks because the tongue tip is a non-crucial articulator. It's moving, but it's not crucial for the bilabial segment. After the vowel, on the other hand, it's the opposite pattern. Now the tongue tip is crucial for the segment N, which can be seen as the tongue tip creates a posture delimited by a rapid slowing down, a deceleration peak, and afterwards a rapid gaining of speed and acceleration peak. This time the lips are the non-crucial articulators. They're still moving, and there is some kind of posture, but with almost no change in velocity, which is evident by the acceleration signal. When we compare these two consonants, we see that the deceleration and acceleration peaks of each of the crucial articulators align very nicely with the acoustic segment boundaries in the bottom of the figure. So what I've been doing lately is to test this hypothesis under different constraints. So far, I've been using mainly two simple ways of measure articulation and acoustics, which is either to investigate the timing of the acceleration peak to the boundary, the segment, or I look at how well the whole steady state of the articulator and the duration of the segment correlates. So I'm going to show you some results. First is the timing. It results on timing and place of articulation. So we know that the crucial articulator for N is the tongue tip. And so now here are 4 target words where either the tongue tip is a crucial articulator or the lips are a crucial articulator. These target words have been put in a sentence for speakers to read with a leading question so that these words are already given information. There's another word who is the new information. So these words should not attract any phrasal stress or higher prominence level, ideally. We have 18 Swedish speakers that were recorded in a EMMA system, and data was collected on a number of articulators, including tongue tip, lips, lower mandible, and tongue dorsum. So if we measure the acceleration peaks on the tongue tip, both in words with an alveolar segment and with a bilabial segment, we would probably get very nice timing for words starting with an alveolar, and not so great timing for the words starting with a bilabial. And indeed, this is what we find. So 0 marks where the timing of the peak is, the acceleration peaks, and the boxes are the timing of the segment boundary. So the first segment in Nanna and Namna aligns very well at onset with the tongue tip deceleration peak, and at segment offset with the tongue tip acceleration peak. This pattern cannot be seen in mamma and manna, where the tongue tip is a non-crucial articulator at word onset. So let's see if the same pattern is for lips. So we find the opposite pattern for the lips. If we measure the acceleration peak and deceleration peak on lips, we find in mamma and manna a good alignment between the deceleration peak and the onset of the segment, and good alignment between acceleration peak of the lips and the offset of the C1 segment. So this pattern is because the lips are the crucial articulator in words with bilabial segments. So since this pattern of timing of the acceleration peak and the segment boundary can be seen both for lips and for the tongue tip, means that it's valid across places of articulation in consonants. So what's the deal with manner of articulation then? Well, speech postures of the articulators seems to be delimited by these acceleration peaks. Consonants are really ballistic movements. So the nature of this movement, meaning the manner of the articulation, could affect this relationship between the acceleration peak and the segment boundary. It could be less straightforward. So this is ongoing work, and I don't have much results to show you, but I'm going to give you one example of a plosive. So let's take a look at the lower lip acceleration for production of the consonants in the word papa. So here you have Emma sensor on the lower lip at the bottom in the figure. So it's moving up for the constriction twice in papa. And on the second row from the top, you have the acceleration signal. And we can see that there is a deceleration peak at the start of the plosive. And please note that this is not at the segment boundary, because this is actually in phrase initial position, and I mistakenly put the boundary too early, actually. So I could shift it now when I know when the consonants really start. Anyway, there's another deceleration peak for the second consonant in the word, which aligns quite well with the boundary between the vowel and the consonant. And then for the acceleration peak, the first one aligns not at the start of the vowel, but at the start of the release. And the release of the plosive. So, and at the second consonant, the acceleration peak, although it's a peak with less magnitude, it does the same thing. It's at the start of the plosive burst. So this is just one example of how we may find a similar but less straightforward relationship between the acceleration peak and the segment boundary in this different manner of articulation. So we need to look at each manner of articulation differently, I think. And the variety, not only on the timing, but also on magnitude of the acceleration peaks, still remains to be investigated. So this is ongoing work. But now we're moving further ahead. So let's take a look at what happens before and after these crucial articulators form the consonant segments. Well, normally we have a vowel segment. Here is a figure on a CVC sequence. And in the figure, you can see the deceleration and acceleration peaks are at the edges of an articulatory posture. So this is the same thing as a steady state. There is a still movement here. So the word is the Swedish word mamma. So the lips are crucial articulators for both C1 and C2. And again, it's lip aperture, so the lips are closing during the constrictions. And since the acceleration peak marks the offset of C1, while the deceleration peak marks the onset of C2, the vowel segment in between, when we measure it in this traditional way, a vowel segment is really the distance between two postures made by the crucial articulators. So this is another hypothesis to be tested. And what I've done is that I compare this distance to what the tongue is really doing, because the tongue is a crucial articulator for the vowel. So let's look at some tongue acceleration data. We usually talk about vowel space for vowels, but the tongue, as we know, are also making a constriction in the vowel space. This follows previous work on vowel constriction location, which is similar to constriction location for consonants as well. So here is an image to explain what I mean. This is, again, a sensor moving in time, vertical position up and down. It's a sensor in the back of the tongue. So it's going down for a position during an open vowel, basically. So as it gets closer to its position, it slows down, and then it stays during the open vowel, the tongue does, and then it leaves the position, and there's an acceleration peak. So I measured this interval, and I compare that with the duration of a vowel segment. So again, using the EMMA data on the 18 Swedish speakers, we find some results. Again, acceleration peaks are now are 0, and the boxes are the segment boundaries. So the acceleration peaks, both the deceleration and acceleration peak. Okay, so the deceleration peak at onset lags behind the segment boundary. And at offset, the acceleration comes earlier than the segment boundaries, the boxes. This tells us that the tongue body acceleration peaks of this constriction of the tongue body are not related to the duration of the vowel segment. Instead, the duration of the vowel segment is much longer. It's about 60 to 80 milliseconds longer than this tongue posture interval. So what does this mean? Well, the vowel segment durations seem to actually be governed by when the crucial articulators of the consonants are making constrictions, and not by when the tongue body makes a constriction. So if we consider vowel segments from this more traditional view, they're really the result of when in time the crucial consonantal articulators are made, just like in this picture on the lips. And any differences on the tongue should, in theory, not have an effect on this link. But we know that vowel segments may vary for different reasons. So, for example, between a long or a short vowel, or a high or low vowel, or between tonal contexts. So, for example, in Swedish word accents, this image shows normalized segments in the Swedish word accent 1, which has a falling tone in the vowel, and accent 2, which has a rising tone in the vowel. So this is South Swedish dialect. The rising tone usually displays longer vowel segments than the falling tone, but this may depend on phonotactic context or whether it's a short or a long vowel. Also, the post-stress consonant has been shown to be longer in the falling tone context. And when prominent, it seems that doesn't matter the dialect or the type of tone, all accent 2 words are longer in segments. Basically, it's a complicated pattern. The segments clearly are affected by the tones, but will they also affect the relationship between the vowel and the deceleration and acceleration peaks of the critical or of the crucial articulators? Let's see. So here we have some results on the distance between an acceleration peak on a lip posture, so that's peak acceleration on the lips, and then a deceleration peak on this tongue tip posture. What I've done is that I compare the vowel segment duration to this interval measured on this distance. So it's an articulatory interval measured between these 2 points. Again, it's the same data as before, the 18 speakers, and this time there are more words, 12 words, divided into accent 1 and accent 2. They are word accent pairs, so they have different word endings, but they all have the same word onsets. And this figure shows vowel segment duration on the y-axis, and on the x-axis, it's this articulatory interval measured between these 2 points. And as we can see in this figure, there's an almost perfect relationship for the word accent pair, manna, mannen. And as we measure the distance between a posture on the lips and one on the tongue tip, this makes sense, as they are both crucial articulators in these 2 words. This is also quite good relationship strength for word accent pairs starting with man and mal. And these are long vowels, so you can see here for at least for one of them, the word accent 2, the rising tone condition, as a longer vowel. But the relationship between the acceleration peaks and the segment transitions are still there. There are some outliers though. There are more results in the conference paper cited here, but the results show that the segmental variation, be it vowel length or tonal context affecting duration, does not seem to affect the hypothesis. Longer segments, shorter segments, it doesn't matter. The deceleration peaks and the acceleration peaks of the crucial articulators are still aligned with these acoustic segment boundaries. So as the alignment seems to be there, even if the segments are prolonged, the question is whether this is the case even when words are more prominent, which we know also often entails longer segments. So I'm going to show you some similar graphs again. This time it's the correlation between posture and the segment. In this study, we used forced alignment to obtain the segment boundaries, and we were interested in whether the relationship between the posture of the articulator and the segment would still hold under the effect of prominence. So we compared focused and unfocused condition, which we control were actually significant in duration, significant difference in duration. So on the y-axis, we have segment duration as obtained by forced alignment. And on the x-axis, we have posterior interval measured using the acceleration peaks. So in these graphs, we have the bilabel segment M measured on the lips. And there's a very strong relationship, can be seen in both unfocused condition and in focused condition, even stronger for the focused condition. And compared to the reference line, we see a slightly tilted regression blue line. This actually suggests that the relationship between the segment and the posture interval could be nonlinear. So let's just recap for a second. What does these results tell us? Well, rapid articulatory movements at the segment transitions consist of acceleration peaks. This is valid for crucial articulators. And the consonantal articulators, when they are crucial, can be referred to as segmental articulators. Acoustic segments, both consonants and vowels, are determined by the timing of the acceleration peaks of the segmental articulators, meaning tongue body, a crucial articulator for the vowel, is not a segmental articulator. Place of articulation does not matter, as the phenomena is present at both lip and tongue tip movement. Preliminary results show that manner also seem quite robust, but it depends on the constriction. And segment variation due to prominence or tonal context does not affect the robustness of the relationship between the acceleration peak and the segment boundary. However, there appears to be some type of perhaps nonlinear relationship going on when it comes to prominence that might be related to articulatory effort. So what is really happening when we make a word more prominent? And for this, we need to look closer at the jaw. But before I get into jaw movements, I wonder if there are any questions so far.
If you have any questions, please. No questions so far. Thank you, Gustavo.
Okay.
You can proceed.
Yes, there's no questions so far in the chat.
Okay, I'll continue. So let's get into jaw movements. This figure shows jaw tracing of "I saw 5 bright highlights in the sky tonight." This is from work by Donna Erickson and colleagues. And as you can see, the jaw is lowered more for some of the words than to others. And this pattern is suggested to be directly related to the metrical structure. So when we look at the stress level, we see that the words on a higher stress level also gets more jaw displacement. So sky gets the lowest jaw, while bright and lights with a low stress level has a higher position jaw. But a speaker can also choose which words to make more prominent. What happens then? Well, here I'll show you what might happen to the jaw depending on where you place your focus. So the figure shows how much the jaw is open for one speaker over 6 repetitions. It's more open for rat than for sat, for example. So first we have this broad focus saying that, yes, a cat sat with a rat on a hat. But if we were to ask if there was a dog on the hat, a speaker would correct and say, no, or they would say this actually.
No, a cat sat with a rat on a hat.
Yeah, so let's see what happens with jaw displacement. The rat gets the focus. The jaw is even more lowered. The rat is already a strong syllable, but it's more lowered. And as it is already strong, it's perhaps more evident in relation to the other syllables. So you can notice the very high jaw in hat. This pattern of a lower jaw for corrective focus is quite stable across speakers, also across the sentence position. And for the speaker, it will surely affect the whole mouth cavity, probably differently for different speakers. But I wonder what the jaw is really doing here and how the rest of the articulators are affected by this. So here is a speaker with sensors about to be recorded in the EMMA, and we have data from the lower mandible by the sensor in the middle on the lower incisors. And the jaw or the lower mandible is really creating the syllable. It stays up during onset and coda, and then lowers, or the mouth opens up during the nuclei, the vowel. And we recognize pattern here that we've seen before. It's these fast movements contra the slow movements or steady states. But what about the timing of these acceleration peaks that separates these fast intervals from the slow intervals? So this is a quite complicated figure. I'm going to guide you through it. Here we have lip aperture. Remember the distance between 2 sensors. So going down means the lips are closed. And we have jaw movements. And this is the word mamma. So lips are the crucial articulators for both constrictions. And the jaw goes up during C1 and C2, and then it's lowered during the vowel. The steady states of both the lips and jaw are marked. So we have 3 steady states. And both of the lips and the jaw, they have deceleration and acceleration peaks on each border of the steady states. But as the segmental articulator, here the lips, they're aligned to the segment boundaries. The jaw shows a different pattern. The deceleration peak of the jaw always follows the deceleration peak of the lips, while the acceleration peak of the jaw always precedes the acceleration peak of the lips. This makes the jaw steady states shorter. Also, there are some very different movement dynamics, some differences between the segmental articulators of the constrictions in comparison to the jaw. They just seem to be behaving differently. And this is very interesting to me. And what we have tried to do is that we try to separate the lips from the jaw, and we can see that they act quite differently as well. So here's a study where we used notion of Fitts law to compare the jaw with the lips. Basically, we wonder whether the distance of the movements from a closed mouth to an open of the jaw and the lips could be correlated with the speed of the movements. So Fitts law predicts that this is a linear relationship. Distance should be equal to speed. And we compare this by looking at the displacement, how much it's open and how fast it's moving. And these graphs show data from 4 words that are different in manner of bilabial articulation. Displacement of jaw and lips are on the y-axis, and how fast they are moving, peak velocity, are on the x-axis. And for the jaw to the left, it seems that it doesn't matter what type of constriction, the jaw does the same thing. So Fitts law seems to fit for the jaw. While for the lips, the amount of lip opening doesn't always mean a faster movement. Basically, there are effects by the manner of articulation on the lips, but not on the jaw. So we are really dealing with very different movements here. The lips are part of a ballistic movement. They move into position and then they leave again, which creates this fast interval, a steady state delimited by deceleration peak and acceleration peak, and then another fast interval. And they're possibly not being active until they are crucial the next time. And they are moving partly separately from the lower mandible. The jaw is instead an opening movement. It's a cycle. It's repetitive, but in a different way than the ballistic movements of the constrictions. That's why it's been suggested that the jaw is a syllable articulator. But what happens when these different types of a movement are combined is when it really becomes interesting. And this is what we still need to figure out. So here's a stylized picture where the thick solid lines are these postures, the slow intervals of speech, and the arrow signifies the fast intervals of the articulators. And this figure is based on the results I've shown you today. So we have acoustic segments on the top. The vertical rectangles show the duration of a segment, and we see that the posture of the crucial segmental articulator aligns well with a consonant. In this CV sequence, that means we have 2 ballistic movements. And below there is the tongue body, lowering in this case for an open vowel. And we know that the tongue body posture is shorter than the vowel segment. And below that, we have the lower mandible, the jaw. Possibly a syllable articulator with its opening movement. The jaw postures are shorter, always shorter than all of the other articulatory postures. But all of the fast movements are simultaneously. The articulators are always moving fast at the same time, as are the postures. They are still at some point at the same time. And then the timing of the acceleration peaks and the deceleration peaks are therefore very much related. But how and to what extent, we don't know yet. Also, what happens to the timing of these acceleration deceleration peaks when the jaw is lowered, as in focus position? the timing and the magnitude of an acceleration peak might be altered. And I believe that this is the case of the segment variation that we find because of different prosodic environments. So it doesn't matter the reason for segment duration variation, whether it's prolonged or reduced. The relationship between the acceleration peaks and the segment boundaries are still there. Also, different aspects of our human sensory system reacts to different types of movement dynamics. So our vision picks up on speed or direction of a movement, while we listen primarily to acceleration peaks and jerk. So acceleration peaks is just such a wonderful and apparent link between production acoustics and perception. It seems robust to changes in, for example, mandible lowering, place and manner of articulation, possibly also laryngeal production. This still needs to be tested. So I'm not going to leave you with this, even though it looks like this is a summary. I want us to shift gear a bit and end with something more practical. I hope we still have time for this, because we can already predict the articulation of the crucial segmental articulators by knowing that they shape the segments. And we know that the jaw lowers for each vowel. So we could actually predict articulatory movements using a spectrogram or a speech signal with the addition of measuring the jaw. So next, we're going to make some very low-tech articulatory and acoustic analysis. This will be a very short tutorial, which I hope you can use for your own purpose with students. Please let me know if it works or if it don't as well. So let's make some low-tech articulatory measurements. Ideally, each person who does this records their own voice, maybe their first language or the second language. But for now, let's use my recording. I'm an L2 speaker of American English. So what you do is that, okay, let's first listen to it.
Pam had a bat.
Okay, so you segment the sound in prod, and then you paste the sound, the segments like this, and you write
Pam had a bat.
And you write on the left, lower lip, tongue tip, and jaw, for example. It depends on what type of articulators are used in the sound. I use lower lip instead of lip aperture because it's easier to draw. You start with using the info from what we know of acceleration peaks and deceleration peaks. So we will pretend now that we have some sensor on the articulators, and we're drawing how they're moving vertically over time. So if you like, you can start with drawing these vertical lines first to help with the timing of the articulators. And then you make some very thick lines for the postures. So this is an active lower lip articulator, and we know that the plosive posture ends with this deceleration peak at the start of the release. So you can draw, so you can just stop it about there. And then you draw the rest of the trajectory while it lowers for the vowel. And then you just continue in making these constrictions. You know, there's going to be a posture for M as well, and for B. Yeah, and then it goes, the lower lip goes down for the vowels. So you can do this also for the tongue tip. And you can see that there are two tongue tip constrictions in this phrase. So the tongue tip goes up and shapes a posture in the middle, and then there's quite a long posture, phrase final. The tongue tip is not very active unless it's a crucial articulator. So because of this, I just made it not move at all, actually, but perhaps it really do follow the vowel movement a bit since it's attached to the tongue. But you can do as you like. Next, we're going to measure the jaw. So let me introduce to you our measurement technique, which is a pen. So now it's time to measure the jaw by doing a very simple trick with a pen. First, you can listen to the sound perhaps and try to mimic how you recorded it.
Pam had a bat.
So you put your pen just with a distance from your chin. So when you speak, the chin will touch the pen only when you have a prominent syllable. Pam had a bat. So I can feel that it's touching the pen during Pam and during bat. So then you can draw these low postures for Pam and bat. And these are always shorter than the segment and shorter than the other postures. Because the deceleration peak always follows the other articulator's deceleration peak, and the acceleration peak always precedes. Okay. And then we know that the other syllables has quite a higher jaw, so I'll just put them like this. And because the chin did not touch the pen, right? And we know that the jaw stays up during the constriction, so let's make some short, steady states here as well. So if we remove the vertical lines, now you have your very own articulatory measurements and some acoustic speech and the jaw lowering just using this simple trick with a pen. So I'm just going to show you one more thing that's very cool with this. You can read this phrase differently, and then you can compare figures. Here's the same phrase, but I read it like this instead.
Pam had a bat.
So focus has shifted. And if you draw the trajectories in the steady states, they will look quite similar, except the jaw will now be more lowered on had. Let's try it. Pam had a bat. Yeah, so I'm touching the pen during had. We can put them on top of each other and do some simple analysis, comparing the effect of the lowering of the jaw in different positions. So the sharper colors, that's the phrase on the top. The lighter colors on the bottom. So you can see, for example, that the steady state of the tongue tip is much later, which has to do with a longer vowel, which in turn has to do with a lower jaw. And the B in bat as well seems to be related to the timing of the jaw lowering in bat. I think that this exercise might be a good way to talk about the effect of articulation and segment duration and how prosody affects it. So I hope you will try it out. And again, please contact if you have any questions or comments on segment art. And here are all the references for today's talk. And thank you so much for listening. And I would love to answer some questions if you have.
Thank you so much, Malin. And please, you can ask using the YouTube chat, please. Anyway, if we don't have questions from the YouTube, I have at least one comment, one question.
Yes, Plinio, I think you can. I think you can start with your question while we wait for people to put questions. Oh, okay.
Okay. Thank you so much again. And it was very nice to see, mostly at the end, things that we're trying to do with Donna and Fujimura, Osamu Fujimura. It's very nice. Thank you so much. And the fact that the peak velocity were more convincingly related to acoustics, at least if I understood correctly, from the jaw data, the peak velocities were more related with acoustic information from the vowels, if I understood correctly. Is that so? When you measure peak velocities for the jaw, it seemed to be more closely related to vowel onsets, at least, I think. Don't you think?
Yeah, possibly. I don't think I measured that, but you're probably right.
The jaw fallings probably was much more related to vowel onsets, I think, from your slides.
Yeah. I mean, this figure kind of shows that there is this figure on the top is one speaker saying
Mm-hmm.
mama, I think. So
Yeah.
the peak velocity is kind of line here. But
Yeah.
I mean, the vowel segment, the start of this vowel segment is the peak acceleration that's going on here of the lips. So I'm not sure if the peak acceleration is related to peak velocity of the jaw. These two, the peak velocity of the lips and the jaw, are more related.
Mm-hmm.
So I'm not sure about peak velocity. Peak velocity is really, I mean, there is a movement change, but there's not, it's a steady course. It's a fast movement, but there's not a lot of changes going on. It's just changes of position.
Okay.
So the acceleration peak is just much more, yeah, that's the transition, is because of the acceleration peak.
And have you looked at coda consonants as well or not? The
Yeah,
behavior of coda consonants, yeah?
Yeah, I have as well. I didn't show you now, but
Okay.
yes. So the
And do you think that these
so
jaw patterns will change a lot when you change the vowel? Because you showed us data from with R or I, but do you think if you have data from high vowels like E, it could be different? Because it seems that the displacement of jaw is much less in this case, don't you think?
Yes, the jaw lowers less for it. So the jaw pattern, the jaw displacement pattern is affected by the type of constriction in coda and onset and the type of vowel and other things as well. There's a lot of effects. So you need to control for that. I didn't talk that much about the jaw lowering now, but I know Donna's talk has way more information about that. But I mean, how to say this? I don't think that the relationship between the segment and the acceleration peaks of the consonants are affected by the lowering of the jaw or the type of vowel. That relationship is just very, very solid.
Okay.
But the timing of the peak, and that's also determines the duration of the segment, is very much affected by the jaw lowering. So we will there was some, I mean, there are some duration effects from the vowel because of the jaw, I think. And yeah.
Nice. You have a question here from the first question from Julie was already asked by myself. I just did it. But Oliver Niebu has a question for you.
Oh.
Or a comment, I don't know. The two things, I think. I think that the term posture makes more sense than the term steady state because the interpeak sections are actually not steady in the strict sense. Are the difference between C and V posture intervals in terms of their degree of steadiness, of jerkiness? You can read if you prefer.
Is it in the chat or?
Yes, okay. It's in the chat.
Yes.
Thank you.
It's the last question.
The posture makes more sense in the term state. Okay, so I think that the interpeak sections are actually not steady in the strict sense. Differences between C and V posture intervals in terms of the degree of steadiness or jerkiness. So the thing that so how to comment this, the type of terms, what I think I'm using terms from that are mathematically defined. Okay, so for example, a posture is not perhaps mathematically defined, but a posture is defined as something that has a lot of movement on either side. So that's just one way of defining it. And then a steady state, I mean, there are different ways of defining it, but yeah, it's a good question. What's the best term to use, perhaps? And what about these intervals, whether they are more or less steady or jerky? that's also interesting because what about, let's look at this one. There are more levels to this. There are more movements. So the steady state here, the posture or the steady state, it's not actually perfectly still. We know that the articulators are never still. And there are some jerks after the deceleration peak and also some jerks before the acceleration peak. So of course, it remains to be seen exactly what's going on here and what we're interested in. But I would say that the definition of a steady state or a posture, whatever term you like, is that they are not jerky, I would say, at least. Does that answer the question? I hope.
Okay, thank you. Other questions? Comments?
Oh, in the chat, no, there is no more question in the chat.
Oh, no.
The other question was already answered, the first one.
Oh yeah. Okay. Thank you. Yeah, it's it's a systematic investigation. So I'm taking one vowel and one segment at a time.
It's normal. It's too much things to do. It's very complicated. So many things to correlate and to coordinate.
It's quite. I understand it's quite dense, but I think it's
I was very impressed by the fact that when you did a focus on rat, I think the jaw was less variable. The focus word, the jaw displacement was less variable, and the greatest effect was on the post-stress position. Was the greatest effect.
Yes.
This is nice because it seems to show that. The domain, let's say, of focus is not only the focus word, but also the vicinity, and mostly the post-stressed one, because it creates a greater distinction between the focus word and the post-stressed one, post-focus one. My impression. But the fact that it's so less variable, it's very intriguing, because normal people say that focused things are much more variable than unstressed and unfocused.
You're right. Yeah.
Probably because it's one single speaker that is very experimented speaker, I think. It's Donna or you, I don't know.
It's Donna, and I mean, this is just preliminary analysis. We have more speakers, but when we shift the focus to this, so we have tried with all of this. So did a dog sit with a cat on a hat, and the jaw pattern just follows. The strongest syllable is always the one with the focus on.
Okay. You have a comment here. Oliver was thinking about how your research and findings relate to things like anticipatory or carry over a co-articulation.
Yes, I would say that everything in the mouth is connected. So I think that this is co-articulation. I mean, articulation is co-articulation. Speaking is co-articulation, but I know what you mean. Co-articulation is a specific thing. If the jaw is lowered here in the middle, this means that it affects how the tongue body, either the start of the position of the tongue body or where the target is of the tongue body. So that would affect when it has to start to move, and that would affect when in time during the consonant it's starting to move. So yes, we can find co-articulation patterns, differences, whatever thing we are changing in the articulation, I would say. But exactly how it's affected, yeah. I have to keep working on the model to understand that, yeah.
Yes. Thank you. It's about 2 p.m. here in Brazil.
Yep.
And I would like to thank you again, Malin, for this wonderful lecture, and ask our public for being here with us. And later on, we'll make available the link to other people wanting to see you during this lecture. Thank you so much. Have a wonderful afternoon to you and to all other people here with us. Thank you so much.
Thank you.
Thank you.
Thank you, Malin. Bye-bye.
Okay,
Bye-bye.
bye.